Hello friends, continuing with chapter of current electricity. Today we take up sixth part as per the mind map, that is measurement of resistance. Today's topic is measurement of resistance. The instrument is Wheatstone bridge, with which we measure the value of resistance. Now introduction. C.F. Wheatstone, a British physicist, developed this bridge for the first time in 19th century to measure unknown value of a resistance. Now what is the construction? Look at the diagram. The bridge has four resistances P, Q, R, S connected as shown to form a rhombus. Out of four resistances, three are known and one is unknown. Junctions C and D are connected with a galvanometer G, which is a null detector, and junctions A and B are connected with a source of EMF B dash. Now thick copper wires or thick copper strips are used to connect resistances to avoid inclusion of resistance of connecting wires. Now balanced bridge. How we say the bridge is balanced? The current through galvanometer depends upon the potential difference between points C and D. The bridge is said to be balanced between C and D when potential difference across galvanometer, that is between points C and D, is 0. I repeat, the bridge is said to be balanced between points C and D when potential difference across galvanometer, that is between points C and D, is 0. That is, C and D are at same potential. So either we say potential difference between C and D is 0, or we say C and D are at same potential, they have both the same meaning. Now in this state, ratio of arms resistance is equal, that is P by Q is equal to R by S. I repeat, P by Q is equal to R by S. When the bridge is balanced, this ratio P by Q is equal to R by S. Now derivation of condition of balance in Wheatstone bridge. Now how we derive the condition of balance in Wheatstone bridge? First we are to develop physical situation. Consider the circuit diagram of Wheatstone bridge as shown. Let I be the current flowing through the bridge. Current I divides itself at point A into two branches. Let I1 flows through AC branch and I2 flows through AD branch. Similarly, I1 divides itself into two branches at point C. Let IG flows through galvanometer branch and I1 minus IG flows through CB branch. At point D, IG joins I2 and I2 plus IG flows through DB branch. So this is how the current flow through the circuit takes place. 2. voltage equation for closed mesh A, C, D and A. Let us write using sign conventions. Minus I1P minus IGG plus I2R equal to 0. Let us mark it as equation 1. I repeat, minus I1P minus IGG plus I2R equal to 0. Okay. Now why we have written minus I1P? Because there is fall in potential when we go from A to C. So where conventional current enters P, that end is at higher potential, and where it leaves P, that end is at lower potential. So there is fall in potential. So we write minus. Okay. Now why we write plus I2R? The same way, plus I2R means we go from lower potential to higher potential. Okay, when we move from D towards A, first end to the resistance is at lower potential, and leaving end to the resistance it has higher potential. So there is a rise in potential. So there is a rise in potential. So we write, for rise in potential we write plus, and for fall in potential we write minus. So this is how I have used sign conventions as per stated above. So you have to take care of these sign conventions, especially while using Kirchhoff's laws. Now 3. Voltage equation for closed mesh C, B, D and C. Minus I1 minus IG into Q plus I2 plus IG into S plus IG into G equal to 0, or opening the bracket we write minus I1Q plus IGQ. Similarly here also we open the bracket, plus I2S plus IGS plus IG into G equal to 0. On simplifying we write minus I1Q plus I2S plus IG into Q plus S plus G, bracket closed, equal to 0. So let us mark it as equation 2. Top 4. Balanced condition. When bridge is balanced between point C and D, then IG must be equal to 0, because C and D are at same potential and potential difference between C and D is 0. Therefore IG must be 0. Therefore equations 1 and 2 can be written as minus I1P plus I2R equal to 0, mark it as equation 3, and minus I1Q plus I2S equal to 0, mark it as equation 4, after application of the condition when IG is 0. We write equations first and second after applying condition IG equal to 0 as equation 3 and equation 4 respectively. Now rearranging equations 3 and 4, we have I1P is equal to I2R. Let us mark it as equation 5, and I1Q equal to I2S. Let us mark it as equation 6. So now we have two equations with us, I1P equal to I2R and I1Q equal to I2S. Dividing equation 5 by 6, we get I1P divided by I1Q is equal to I2R by I2S. I1 cancels and I2 cancels, and we are left with P by Q equal to R by S, and is the required condition of balance between point C and D. Now conclusions. When point C and D are at same potentials, then current through CD is 0 and ratio of arms resistance is equal, that is P by Q is equal to R by Now assignment 3.6, question number 1. The given figure shows a network of resistances. Name the circuit so formed. Second, calculate the current flowing in the arm BD of the circuit. So you look at the circuit, you have to find out current through the arm BD. You use Kirchhoff's laws, and then using respective sign conventions you write equations and find out the value of current flowing through branch BD. Question number 2. In the given network of resistances, calculate number 1 electric current flowing through 10 ohm resistance connected across C and D, and number 2 through the whole circuit. Now I give you hint how to solve this. You look at the point C and D. So when C and D are at same potential, it means CD is an open circuit. It means 10 and 20 ohm are in series and 20 and 40 ohm are in series. It means one branch has 30 ohm resistance, 10 plus 20 equal to 30. The other branch has 20 plus 40 equal to 60. So 60 and 30, they are connected in parallel. It means 30 into 60 divided by 30 plus 60, it comes out to be 20 ohm. Then 20 ohm comes in series with 5 ohm resistance. So total resistance of the circuit is 25 ohm, and 25 ohm resistance connected across 10 volt battery. It means the current flowing is 10 by 25, that is 0.4 ampere. So IAB is 0.4 ampere. So this is how you have to solve this problem. Question number 3. 6 resistors, each of value 6 ohm, are connected together in a circuit as shown. Number 1. Calculate equivalent resistance across points A and B. Second, if a cell of EMF 3 volt is connected across AB, compute the current through arm AB and DF of the circuit. So arm DF, if you look at these 5 resistances with arm DF, then it is balanced Wheatstone bridge, because the ratio of arm resistance is same. Therefore you can treat FD as an open circuit and current through FD branch is 0. So FD can be treated as open circuit. So it means 6 plus 6 is 12, and 6 plus 6 is again 12. So 12 and 12 in parallel. So equivalent resistance is 6 ohm, again 6 ohm and 6 ohm in parallel. Then it is 3 ohm. Total resistance is 3 ohm. So if a cell of 3 volt is connected across AB, compute the current through arm AB and DF of the circuit. So current through arm AB is 1 ampere and through arm FD is 0. So this is how you have to solve this problem. Now meter bridge. First, introduction. Meter bridge is a modified form of Wheatstone bridge in which two resistances R and S are replaced by 1 meter length of manganese wire. It may be manganese, it may be constantan, or it may be any alloy wire having high resistance wire. And point D is made slidable on wire. Resistance P is replaced by X and Q is replaced by Y. 2. Construction of meter bridge. It consists of two resistances X and Y in place of P and Q respectively, together with 1 meter length of wire in place of R and S of Wheatstone bridge as shown in diagram. The 1 meter wire is of uniform cross-sectional area and is either of manganese or constantan alloys. Galvanometer is connected between C and D and battery between A and B. Okay. Now for reading lengths of wire, a calibrated scale from 0 to 100 centimeter is provided with the wire. Contact D is made so that bridge could be brought in balanced condition, that is slidable on wire. Basically, meter bridge is modified form of Wheatstone bridge, hence follows the principle of Wheatstone bridge. 3. Principle of meter bridge. When meter bridge is balanced between C and D, galvanometer shows no deflection, then the ratio of arm resistance are equal. That is, X by Y is equal to L over 100 minus L. So this part is L and this part is 100 minus L. So ratio of arms resistance equal means X by Y is equal to L by 100 minus L. Since ratio of arms resistance become equal in this situation, therefore X by Y is equal to L over 100 minus L. Now 4. Measurement of unknown resistance. Suppose X is unknown and Y is known. By sliding point D over the wire, null point is detected in galvanometer. That is, null point is reached when galvanometer shows zero deflection. In this situation, bridge becomes balanced between point C and D. Then Y and L are recorded. So this Y and this L are recorded. Now since ratio of arms resistance become equal in this situation, therefore X by Y is equal to L over 100 minus L. Now because R is equal to rho L by A and S is equal to rho 100 minus L by A. So therefore R and L are in direct proportion. So we have in place of R we write L, in place of S we write 100 minus L. Other parameters get cancelled while taking the ratio as P by Q equal to R by S. So R by S, in R by S, rho by A on both sides will cancel. So we are left with L over 100 minus L. So this is how we use the principle, that is X by Y is equal to L over 100 minus L, because resistance of the wire is proportional to length, directly proportional to length of the wire. Okay. Assignment 3.6 continued. Question number 4. Draw a circuit diagram using a meter bridge and write the necessary mathematical relation used to determine the value of unknown resistance. Why can't such an arrangement be used for measuring very low resistance? Question number 5. Why thick copper strips are used in meter bridge for connecting resistances? Question number 6. Why manganese or Constantan wire is used in meter bridge? Assignment 3.6 continued. Question number 7. In a meter bridge, the balance point is found to be at 39.5 cm from one end when resistance Y is 12.5 ohm. Number 1. Calculate value of X. Number 2. Determine the balance point when X and Y are interchanged. Question number 8. The null point is found to be at a distance of 33.7 cm from end A. The resistance Y is shunted by a resistance of 12 ohm and null point is found to be shifted by a distance of 18.2 cm towards B. Calculate values of X and Y. Assignment 3.6 continued. Question number 9. In a meter bridge setup, the null point is found to be at 60 cm away from end A with X and Y in position. When a resistance of 15 ohm is connected in series with Y, the null point is found to shift by 10 cm towards the end A of the wire. find the position of the null point if a resistance of 30 ohm were connected in parallel with Y. Where is the answer? 75 centimeter. So here we finish with this topic, sixth topic, measurement of resistance. Next time we'll take up measurement of EMF and PD of a cell. Till then, goodbye.